Okay, so today I think we're going to visit Hawaii for a little while. And again, you guys don't have to take notes through this. If you need any of this info, it'll be on the PowerPoints that I'll put up or the video that'll come up after this. But we can just spend a few minutes kind of going through. I'm not going to go way back in Hawaiian history. I'm going to talk about the lead up to the eruption that happened in 2018. So just a couple of years ago, Hawaii had kind of a big eruption that ended a 35-year period of activity there. So I'm going to talk about that period of activity from, let's see, when was that? 1983 to 2018. And then in a week or two, we'll talk about what happened in 2018 that kind of wrapped up this whole eruption sequence. So just to give you a little familiarity, up on the top here we have the Hawaiian island chain. It consists of several islands. The youngest island here is the big island of Hawaii. That's where all of the modern day eruptions are occurring. We'll kind of take a closer look at the big island here in a minute. But one thing you can see as you march to the west across the Hawaiian island chain is that the ages of the islands get gradually older. So Maui, next island over, has the rather famous extinct volcano Haleakala. It's one you can bike down. It's up over 10,000 feet. It's about 1 million years old. You go to Molokai, another half to 1 million years older than Maui. Oahu, where Honolulu is, rocks there are 2 to 3 million years old. And by the time you get to Kauai, you're looking at about 5 million year old lavas. So you get progressively older as you move to the west. These islands all used to sit over the hot spot, which today is under the Big Island. And then as the plate has moved to the west, it drags those islands off the hot spot and they become progressively dormant. So you see, Kauai is the last exposed of the Hawaiian volcanoes, but if you look at a map of the seafloor, you can see that the Hawaiian chain actually extends all the way to Midway Island, which is out here, site of a lot of naval activity during World War II. And then it even continues on to the coast of Kamchatka. And as the islands get older, the seamounts that are beneath the ocean surface get older as well. By the time you get up to the oldest part of the chain, here by Kamchatka, it's about 65 million years. So that hotspot has been around since the dinosaurs were extinct. So it's a long-lived mantle plume. Right now, the plate is continuing to move to the west. So eventually the Big Island is going to get pulled off the hotspot as well. And there is a new island that's developing just off the coast of the Big Island. It's called Loihi. And if it keeps erupting beneath the ocean at the same rate it is now, it will be exposed in about 10,000 years. So it's out there, looming beneath the surface, ready to move on up and take the place of modern Big Island of Hawaii. So here's the Big Island, Google Earth view. And the Big Island has a number of volcanoes. So this is the Big Island. If you've ever been there, kind of the main city on the Big Island is Hilo. It's 15 miles from kind of this site of activity that we're going to talk about in a minute. To the far end of the island, you have Kohala. It's probably dormant, might be extinct. The difference between extinct and dormant, extinct means it's never going to erupt again. Dormant means, it's probably going to erupt again. Not for sure whether some of these are completely done with their erupting or whether they might squeeze out another small eruption or two. Just don't know at this point. Mauna Kea, one of the tallest of the Hawaiian volcanoes. We don't know if it's dormant or extinct. There's lots of telescopes sitting up on top. It's one of the Keck telescope that we spent quite a bit of federal money to put up a few years ago. Great place for observing. Hualalai, which is over here, the other big town on the Big Island is called Kona. And Kona sits right at the base of Hualalai. That erupted just a couple hundred years ago. So still has some potential for activity. The big monster volcano on the Big Island is Mauna Loa. Last erupted in 1984, spectacular eruption that sent lava within a mile or two of the city of Hilo. Came roaring down a valley. People in Hilo thought they were going to get inundated with it, and luckily it just stopped. So it was a few week eruption. It didn't last super long, but Mauna Loa is due for another big eruption. It tends to erupt fairly frequently, but now you can see it's going on 40 years since it's erupted. So that leaves us with, and just as a note too, Mauna Loa is the biggest mountain on Earth from base to top. It's over 13,000 feet high, but as the flanks extend off into the ocean, it goes down to 17,000 foot depth. So when you add together the submarine part with the terrestrial part, you end up with 30,000+ feet of volcano. So it's a pretty impressive feature. For the last 35 years or so, all of the activity in Hawaii has been centered on this volcano right here, and that's Kilauea. And Kilauea has had several sites of eruption. It's erupted up at the summit. The summit's about 5,000 feet above sea level. Summit eruption was about 10 years. I spent a lot of time there with a lot of UNC students through those years. Kilauea Iki, nearby, erupted in 1959. A pretty spectacular eruption. It sent a fire fountain up 1,500 feet. So it just squirted basaltic lava straight up for a while. And then there was a landslide that sort of came over part of the vent, and it directed it like a garden hose straight across the valley against the canyon wall. Pretty impressive stuff that's left behind, and filled up this low area with a bunch of lava and made a lava lake out of it. Mauna Ulu was a 3-year eruption. Erupted right here, sent lava flows down to the coast. Pretty impressive feature. It's not going to work tonight, is it? And then finally, Pu'u'o'o. This is the site of the longest lasting eruption at Kilauea in recent memory. It started in 1983, sent lots of lava flows down to the coast. That's what this is supposed to indicate here, the little steam coming off the ocean. And then there was a crater with a small lava lake here as well. So that part of the volcano erupted for about 35 years with only a couple of brief day to 2-day interruptions. So it's been active for a long, long time. All right, so let's I'm gonna have to stand over here. Some of those lava flows have tried to enter some nearby communities. Lots of people want to live in Hawaii. Hawaii is a great place. Hawaii is also an expensive place. And if you want to go there and live on a dime, you can. But you get to buy land along the volcanic rift zone, which will erupt from time to time. So there's lots of people that live really close to these sites of activity. And in fact, what happens is their houses get overrun, and then they just build on top of the new lava. And that's all they can afford to do. You can't get insurance for it. And if you do get insurance for it, we'll talk about it later. It's really weird, some of the rules as to whether you get paid or not. Actually, it's one of my favorite stories. So when you see a house that's about to be burned by lava in Hawaii, you will always see a person there watching it. And it's usually an insurance adjuster. And the way insurance law works, I'm not kidding about this, absolute truth, is if the house goes up in flames before the lava physically touches it, you're covered by fire insurance. But if the lava touches it first, you get nothing, because that's the volcano and that's an act of God, and you cannot get insurance for the volcano. So sadly, what happens is if people think their house is going to get torched, they light it on fire before they leave.
That's what I would do.
So that way they're assured, and it's difficult because no one's going to come in there and sort of check to see where the fire started because it's getting buried by lava. So, I don't know. They argue it's a victimless crime, but I don't know. So anyway, that's just how insurance works there. But you'll find lots of people who live really close to these eruption sites.
How do you get that job of the guy who sits there and just watch people's houses go on fire?
I don't know,
Become an
but
insurance adjuster.
but I wouldn't want it. Yeah. I mean, it's always cool to watch stuff burn down, but I don't know. Watching people's houses burn, not so cool. Okay, and then, like I said, the site of some really cool activity that we'll talk about happened up at the summit of Kilauea over a 10-year period, and we'll look closer at this area here in a second. Okay, so from 2008 to 2018, there were a couple of different sites that were erupting lava at Kilauea. So that present should no longer be there. It was 2008 to 2018. So that is up at the summit. There's a little caldera up there. If you guys remember, calderas are collapse features. Usually they're associated with big explosions, big explosive eruptions, but you can also get them with these basaltic eruptions where they drain out so much material that the area above it collapses. So we're going to zoom in on this area here in a minute. So just a little background about Kilauea. It's a few 100,000 years old, so it's been sitting on that hot spot for under 500,000 years, and that sort of makes sense when you look at the progression of the other Hawaiian islands. Those islands sit over it for 1,000,000 years or so, and at that point, plate tectonics pulls the volcano off the hot spot, and a new site of eruptive activity flares up. Mostly what you get when these eruptions happen, 99% of them are very quiet. They just erupt lava flows, and lots of lavas, but at a really slow rate. The overall eruption rate over the last 35 years there is about a cubic meter per second. So this much lava coming out of the volcano every second. That's not super fast, but you know, give it 35 years of lava piling up on the surface and it can create quite a mess. It can create new land. It has created some new land along the coast. There can be violent eruptions. They're pretty rare, but when they do happen, they're pretty spectacular. You've probably heard of King Kamehameha. He ruled the Hawaiian Islands for a while, but actually his brother-in-law went to war against him on the Big Island at one point in time, back in 1790. And as his brother-in-law was heading towards Hilo, where King Kamehameha was, they went over Kilauea volcano, and just as they went over it, Kilauea erupted explosively and wiped out Kamehameha's brother-in-law and his whole army. So the volcano plays a pretty important role in Hawaiian history at time, and you know, it's an integral part of the culture for the native Hawaiians. Mostly it's quiet, but it can be explosive, and that's something you have in your back of your mind when you live there or when you work there. So the summit caldera, which we'll spend a little time talking about, it's pretty big. It's about 3 to 4 miles across, and there's lots of features within it as well. And it's a collapse from magma being withdrawn for some of these longer-lived, quiet lava flow eruptions. So Halemaumau crater is where the goddess Pele is supposed to live. And that is a collapse that sits inside the caldera. So you have the caldera, which is a big, wide, 3 to 4 mile in diameter crater. And that crater's pretty deep. And then inside that crater is another crater called Halemaumau. And it's about 1 mile across. And it's a pretty impressive feature. That's where the goddess is supposed to live. And back in the 19-teens and 20s, there was a lava lake that sat in that thing for several years. Mark Twain used to go there and watch it. That's when they put the Jagger Volcano Observatory and Museum right on the edge of it so that the people working there could look into a lava lake all the time. Pretty cool place to work. And then in 2008, this is really weird, another crater developed within Halemaumau. So you've got Kilauea crater, big crater, 3 miles across. And then you have Halemaumau crater, which is inside Kilauea crater. It's a mile across. And then inside that, another crater popped up. And it was only a few hundred meters across at one time, and it had a lava lake in it. So initially it was small, and then over time it grew and grew and grew, and actually got quite large at one point. I'll show you some video and some pictures here in a minute. So this lava lake and pit sits inside Halimau, which sits inside Kilauea caldera, which sits on the top of an active volcano. So it's a lava lake in a crater, in a crater, in a crater, on a volcano, on an island. So you got multiple generations of things going on, and I'll show you a little image of this here in a second. So here's an aerial view of the summit region. So there's Kilauea caldera, 3, 4, 5, 6 miles across, depending on which dimension, and it's from collapse, draining out of the lava from beneath it. Halimau, it's about a mile across. A mile's pretty big, and it's another collapse pit. And then inside that is another pit, which popped up in 2008 and had a nice, really active lava lake sitting in it. So here's where the Hawaii Volcano Observatory is, and the Jagger Volcanic Museum. It's part of the Hawaii Volcanoes National Park. Unfortunately, because of the eruptions in 2008, there were a lot of magnitude 7 type earthquakes, lots of ground damage. They've had to vacate this now. So you can no longer go to it, unfortunately. The scientists who used to work at the Volcano Observatory, that Volcano Observatory has now been moved down to Hilo, 15 miles away along the coast, which is really unfortunate. It was a great place to work. It was a great place to visit. Tourists really loved it because you could just go up there and look in and see all this activity. I talked about that eruption, Kilauea Iki, in 1959. That's right here. That's where they had that 1,500-foot lava fountain. And then eventually so much came out that it filled this old crater with lava a couple hundred feet deep. So a pretty impressive place. The other neat thing about this is that this has nothing to do with volcanology, but it has one of the greatest rainfall gradients on the planet. So if you look, you see this is all green over here, right? That's a rainforest. It gets several hundred inches of rain a year. From the prevailing winds that come off the ocean, comes up the volcano. As it rises, you get the orographic effect, and rain dumps out. And then you hit the summit of the volcano, and those winds go down the other side, and as they go down, you get a rain shadow. So you can see that from here, green, to here, no green. This is a desert, and it's a true desert. It gets less than 10 inches of rain a year. And you can actually sort of sit here, and you can see it raining over here constantly. And you'll be working in clear blue skies. It'll be like that all day. One of the weirdest places you can go, but interesting at the same time.
And how high is the summit?
Well, 5,000 feet.
Okay.
Yeah, so
not that big.
well,
I mean,
we're
it's
at 5,000
big,
feet
yeah.
here. It doesn't seem like much, but 10 miles away is the ocean.
Yeah.
So that water, that air comes out saturated with moisture,
Right.
lifts 5,000 feet in the middle of a couple miles, and that moisture just dumps out constantly. And then by the time it starts down the other side, it starts warming back up and starts sucking the moisture out of the ground. So this is called the Kau Desert, and it's a true desert. You find very little plant life growing over there at all. Really interesting place. So this is what it looked like at night when that pit crater and lava lake were active. So this is Halimau right here, about a mile across. The overlook crater and lava lake was right here, a couple hundred meters across. And then this isn't actually lava, it's actually the glow of the lava hitting the steam that's coming off the volcano. But looks pretty impressive at night. And that's what it looks like during the day. So Kilauea caldera is this edge right here. So it goes like this, it goes way off to the horizon and hooks back around. This is Hale-Mau-Mau right here. It's about a mile across. And then the overlook crater and lava lake that I'll show you up close sits inside of it. So it's a lake in a crater, in a crater, in a crater on a volcano. And then I'm actually standing right next to the Jagger Museum and Hawaii Volcanoes Observatory when I took this shot. So this area right here, prior to 2008, there was a road that you used to be able to just drive around Hale-Mau-Mau. Tourists could go up to the edge. Native Hawaiians would throw bottles of gin in there and other offerings for the goddess. And then when this eruption started, so much gas came out, it would always blow over the road, and it wasn't safe for anybody to be there. If you spent more than 20 seconds in there, you could pass out and die. So very few people ever got to actually see the lava lake. And sadly, you couldn't see the lava lake very often from anywhere that you could safely visit because it was down in the crater far enough. But because I do research there, I get to go right to the edge of it frequently and with some students. Not the safest place I've ever been, but definitely one of the coolest. So this is what it looks like from the other side. So this is Hale-Mau-Mau crater right here, and you can see it's pretty deep, several hundred feet deep. And then here's the overlook crater, and even that is pretty good size. You could fit Mile High Stadium inside that. You could put the world's biggest cruise ship inside that. And just for scale, that's actually me and a student sitting up there. So you can see with the scale there, it's a pretty big place. And over time, this crater got bigger and bigger and bigger. So it was active about 10 years, and you can see these steep walls. They would collapse into the lava lake every so often and enlarge the crater over time. So it grew from being just a tiny 100-foot wide crater to being big enough to consume all of Mile High Stadium if you wanted to stick it in there. I'm not a Bronco fan, so I think it'd be cool to stick it in there. All right. So here's a image, and watch this section of wall over there. So it falls in, and when it hits that upper crust, what it does is the gases sort of accumulate beneath those darker crusts, and when the rocks fall in it, it breaks that up, and the gases jet out explosively and throw crap all over the place. And this is actually where we worked. So I was there a couple dozen times over 10 years and never had any trouble until the last time I went. And one of these happened, and we had to go duck behind some big rocks, and it was pretty impressive. But now you can sort of see what happens for a little while. It goes kind of crazy and bubbles and super ridiculous. And the size of it, this looks small, but it's enormous. And that stuff is really hot. So there's several permanent cameras that were set up there. I don't think anybody was there when this happened, so it was just captured by one of the cameras that runs 24/7 there. So there's regular video cameras, they have thermal cameras, they have gas meters, they have all sorts of different things to monitor what's going on. This is about an hour's worth of video I took with my GoPro and right at sunset. So you can see how the patterns kind of change on the surface of the lava lake. And it gets more impressive as it gets darker because the light from the sun doesn't play a role, so all you see is the infrared and thermal signature from it. But again, pretty impressive. Now when you're actually looking at it, it moves super slow, so this is sped up quite a bit, but looks a little like plate tectonic stuff. Well, it jumped ahead, but one of the things that we did is we brought LiDAR out there. LiDAR allows you to take super detailed images of the topography of the area. So this is a LiDAR movie we put together. What's kind of interesting is there's the crater and lava lake, and as you pan around, something that you can't really see real well through the smoke and plume was that little bit right there. That was an overhang. And became pretty worrisome because it's basically sitting right there, and we were worried that the whole thing would fall into the lava lake while somebody was working. It never actually happened. Pieces would fall off. We never had it go at one time, but it was always a concern when you were working there. So I had a couple students do LiDAR work there over the 10 years. One of my master's students, Adam, did his thesis on it, and it turned out really well. He's publishing a paper on it. Actually, it's being reviewed right now, so did really good work. So let's see what else we have here. So all that activity took place up here at the summit, okay? So that was 2008 to 2018. We'll talk about what happened in 2018 another week. Pu'u'o was active for 35 years down rift. And if you notice all these lavas seem to come out of a linear-like feature. Kilauea has two rift zones. So it has a northeast rift, which starts here and heads off that way. And then it has a southwest rift, which heads off this way. And you can see some recent lava flows that have come out on it. And what's happening is this side of the island has no support. All that's out there is ocean water. So as the lava comes up, this side of the volcano actually pushes out and forms two big cracks. And lava will then move along these cracks. And you never know quite where it's going to pop out. Could pop out at the summit, could pop out here, could pop out here. There's definitely been eruptions that have happened offshore. And it all seems to be connected because during that 2008 to 18 time period when the lava lake was here, one day just out of the blue, there was a small eruption right about here. No warning at all. In fact, there's a campsite right here. And there were some backpackers, and in the middle of the night, crack opened up right through the campground, and lava started spewing out, and they had to be airlifted out by helicopter, which is pretty cool. But as that eruption happened, I'll show you a video of it in a second, the lava lake just disappeared. It just drained and went away. So all of the lava that had been up there got diverted down the rift, came out there, and then as soon as that eruption stopped a few days later, the lava lake filled back up again. So there's a connection, magmatic connection down this rift between all the different eruption sites. It's a pretty neat place. So let's see what I have here. I think I have another video or two. So sometimes the lava reaches the coast, which is pretty spectacular. We'll spend a little time talking about submarine eruptions a couple weeks from now, so I'm not going to talk much about it now. But like I said, a lot of people live nearby, and lava sometimes comes into their yards. And there's always this big dilemma, okay? I've got lava coming towards my house. Is there anything I can do about it? Well, some people try. They get backhoes, and they build berms, and it will deflect the lava at first. Where does it deflect the lava to?
Wherever you point it.
Right, which happens to be your neighbors.
There you go.
So there's this whole ethical question. First of all, should you mess with Madame Pillay and her will? And next, if you deflect the lava onto somebody else's land, should you be held liable for it? So most people don't do it. Instead, they just torch their own house. But that is an issue. Now, if you put a berm up, it might work for a while. But if the lava keeps coming, eventually it's going to move the berm or overtop the berm. You can only stop it for so long. People have tried to use hoses to stop the advance of lava. Just hose the hell out of it, try to speed up the cooling, make it become solid rock. But again, the lava's still going to come, right? And if you stop the lava from hitting your place, it's just going to go to your neighbors. So even that isn't really viewed as being ethical behavior on the Big Island. So, you know, it's just something you live with. And like many places, the people who have the least financial means to recover for this are the ones who are impacted the most. That's where land is cheapest.
How fast is this lava coming? Do they have time to react at all?
Okay, that's a great question. So that lava, if that kills you, you are the world's most pathetic human being around. Because, I mean...
Or you wanted to die.
You could fall asleep in front of it. I mean, the fastest that kind of lava moves most of the time in Hawaii is a walking pace. Back in physical geology, you probably heard of Pohoihoi and Aa. Pohoihoi is it just takes forever. It moves so slow. Aa will move at a brisk walking pace. I mean, it'll move this fast when it's coming down. It just sort of, it's like a steamroller. So, you know, that could be a problem. The one time that Pohoihoi has actually killed people is at a volcano in Africa. It's a steep volcano. There's a lava lake on the top with basaltic lava, just like Hawaii. But every once in a while, and they don't know when, and they don't have good monitoring, the volcano just splits open. The lava lake drains out catastrophically. It's steep slopes. And there, the lava flows have been clocked at 60 miles an hour. And one of them killed 2,000 people. It came into a town of 1 million people, Goma, and wiped out one of the, communities on the edge of town. So horrible way to die. Of course, happened in the middle of the night. But that's about the only time that lava is really going to kill somebody, is real, unique, special situation. This stuff moves so slow. It's not a hazard to human life for the most part, but obviously it can consume a lot of property. So let's see. So this is the South Rift Zone here. This has not been active for over 50 years. There's a couple small eruptions that happened a little longer ago than that. The Northeast Rift has had a lot of activity. So there's that summit area that we were talking about. And there's the rift zones right there. So that's where you're likely to get eruptions that kill away. And then these extend off into the ocean, quite a ways off into the ocean. And there's activity there. It's just that it never gets monitored. So let's see. Gosh. So there's the East Rift Zone there, Southwest Rift, all because that side of the island is unsupported. Now, one thing that has happened in Hawaiian history, I'm not going to talk about it too much today, is that there's been massive landslides off the Hawaiian Islands. And they probably happen where they have these rift zones, because this area is weakened, there's nothing supporting out here, and they've had massive amounts of land that just slip off into the ocean. And there's always been a concern that this could happen. So in 2018, there was a magnitude 7 earthquake, and this whole area on this side of the rift zone moved a meter. It's a lot of movement for that much land. It didn't slip off into the ocean, but there were people who were a little bit worried about it. So again, these summit and downrift areas are connected. They communicate with one another. So let's see. I'm going to jump ahead here. Okay, so this was in March of 2011. This is how the lava lake usually goes. This is sped up quite a bit. And then watch what suddenly happens. The lava lake just disappeared. And that dropped about 300 feet, so length of a football field, in just a couple of hours. And it had never done that. Been around for 3 years, had never done it at all. At exactly the same time, 10 miles away, this happened. The campground is right over here. So you can see the rift right here. The lava's coming right out along the rift. Here's another big crack where the lava's going back in. Pretty impressive. But yeah, if you were out there camping, that would even looked worse than what we went through with the fires yesterday, I suspect. Okay. So we'll talk more about Hawaii in the coming weeks. And in fact, we'll talk about classifying eruptions. I don't know if it'll be next week or the week after. And one of the ways we classify volcanic eruptions is by famous eruption sites. So there is a type of eruption called Hawaiian eruptions. They can happen in other places besides Hawaii. But Hawaii erupts so consistently and most of the time in the same manner that it's an activity that has features that you see happening at other volcanoes as well. Places like the Galapagos sometimes have Hawaiian type eruptions. Okay. So last class, we were talking about melting, okay? So we'll get back into that and we'll finish that up. So we talked about heat sources last class. We have the geothermal gradient. It gets hotter as you go into the Earth because of the original heat that created the Earth. But that alone is not enough to cause melting. So we're looking for ways to heat up the rock more than just the geothermal gradient could. We talked about radioactive elements, right? How that could provide more heat. But yet we see lots of volcanoes along tectonic boundaries. So clearly there's something going on there with tectonics. And we'll get into that, I think, later in the class. Now we know from earthquakes, we know from geochemistry, we know from geophysics, we know from a lot of different avenues that the mantle, the upper mantle, is probably what is being melted to give us all the silicic liquid that comes out of these volcanoes. So we'll spend just a couple minutes talking about the mantle. Like I told you last time, one of the things I really like about volcanology is that you get to use all of the stuff you learned in all of your other geology courses. So you'll get to use petrology and mineralogy. You even get to use stratigraphy and sedimentation when we talk about pyroclastic flows. So I've always enjoyed that because I get to use the things that I learned in all the classes I took. So some of this stuff you've probably seen in some of your classes. So what do we know about the mantle? Well, we know it's solid. We know the upper part behaves brittly and becomes part of our tectonic plates. Our tectonic plates includes the crust, but it also includes part of the upper mantle, the part that behaves brittly. And then we know that part of the mantle behaves ductily. We also know that there's some minerals down there. We have mantle xenoliths that have come up in volcanic eruptions. But we also have sections of the mantle that are exposed up in the crust now. It's kind of cool. How many of you have heard of ophiolites? Yeah, which class did you get ophiolites in?
I think a couple, oceanography and paleoclimatology, because we talked about them.
Excellent. Yeah, so we have pieces of the upper mantle that have been squished, traveled up to the Earth's surface. So we kind of know what we're dealing with, and we can do experiments with some of the rocks that we find there. So again, we know the mantle can behave brittly in the upper section. We know it behaves ductily when you get down deep enough. That's what allows the brittle, solid tectonic plates to move around on Earth. It's still solid, but because of the heat and pressure, it behaves differently when you stress it. And it can move plastically, even though it is a solid. The individual solid grains can shift next to other solid grains. We know that it convects. We think it convects. We don't know exactly how it convects or what it looks like, but various models. If you've had any of Dr. Baird's classes, you know about shallow subduction and deep subduction and all different models for how plate tectonics developed, proceeded, and how it works today. So we know a few things about the mantle. And then we have these places out in the ocean, mid-ocean ridges, where the crust is really shallow. It's elevated relative to the ocean floor around it. Lots of volcanic activity along it. So these are areas where the mantle is unusually close to the surface, giving off a lot of heat. And as we'll see in a minute, they're actually perfect environments for creating melting. We've talked about how difficult it is to melt rock already. You got to get it up to really high temperature. Then you got to pump in all this extra heat to break the bonds. And the natural geothermal gradient just isn't close enough. So we're going to have to do something to get this stuff to melt. Well, mid-ocean ridges do what we need to have done, and we'll get into that in a second. We know something about the mineralogy of the mantle. We know this from mantle inclusions, xenoliths. We know them from ophiolites. We know it from earthquake waves. We know it from geochemistry and geophysics arguments. Now, the deeper we go, the less certain we are about what we know. But it looks like at the depths where melting is occurring, we have rocks with lots of olivine, pyroxene, and garnet. So we can look at these minerals specifically, look at how they melt in the lab, and get an idea of what sort of conditions we need to create magma in that area. So again, how do we know about the mantle mineralogy? We can actually go get pieces of the rock. Even though we can't go to the mantle occasionally comes to us. So we can directly sample it, look at the chemistry, look at the mineralogy. We can do melting experiments. We can create phase diagrams. How many of you have dealt with phase diagrams? You're going to get some in here too. And hopefully, because you saw it in petrology, I'm guessing, when you see it in here, you're going to see it in a different light, I think. So maybe seeing it the second time and seeing how those complicated diagrams actually proceed. Now we're going to actually make something real out of it, so hopefully it will help that concept solidify a little more in your brain, because I know the first time I saw phase diagrams, I could follow it, I could understand it, and then 2 hours later I'd forget it. This hopefully will help you remember it a little better, but we'll get to that. Like I said, we take geophysical measurements, mostly earthquake wave velocities, which tells us something about density, which tells us something about the minerals that are there. And then we can take these samples back to the lab or create samples in the lab that mimic what we believe exists in the upper mantle. We can stress them, we can strain them, we can heat them, and we can try to partially melt them, and then we can try to completely melt them. And we can see what kinds of melts we get under different conditions. And then that helps us come up with ideas on how do we actually melt this stuff. This stuff's hard to melt. What do we actually have to do to melt this upper mantle material that's olivine, pyroxene, and garnet? And then, mention this a little bit, I'm not going to get into it too in depth, but we have meteorites. Many of these probably come from the asteroid belt, which may have been a planet that tried to form, differentiated to some degree, and then fell apart, collided with something, Anyway, it's in a zillion pieces out there now, and some of those pieces sometimes comes here, and we can see different minerals in the different meteors. Some of them are iron rich, like you would expect in a planetary core, and some of them are olivine rich, like you'd expect in a planetary mantle. So it's like looking at the inside of a planet, because it was kind of a planet at one point in time. And then you always have arguments from geochemistry. We have these minerals. We've been looking at them in lab settings for some time. So we know a little about their densities. That when you pair with earthquake wave velocities and things like that, you get a reasonable view of what's going on down there. Always subject to change, because as you go deeper in the mantle, we have less and less information about it. So this is what we're going to melt to make volcanoes. Mostly that upper mantle stuff. We're going to melt olivine, pyroxenes, and garnets. And then once we have that melt, it's got to get up to the surface. And it's not easy for that stuff to get up to the surface. 90+% of all magma that's created never sees the Earth's surface. It's really hard to get it up there. A volcanic eruption's a really rare event.
Except where it's not.
Except where it's not. So this upper mantle, peridotite, mostly olivine. Fair amount of pyroxene, and a little bit of garnet thrown in there. All right, we talked a little about ophiolites. These represent sections of the Earth's oceanic crust and upper mantle. And they have kind of a consistent stratigraphy. So at the very top you find pillow basalts. What do you guys know about pillow basalts?
The ocean ridges, I think.
Yeah, they are the morphology of lava that forms when lava erupts under the sea. They're the most common sort of seabed lava flow feature we have. So they're indicative of eruption into water. Beneath that, you get what are called sheeted dikes. So basically these are cracks filled with basaltic magma. So you can think of them as being the ocean floor that the basaltic magma traveled through to erupt on top of it as pillow basalts. So that basaltic magma comes from deeper down in the section, through these dikes, erupts onto the existing ocean floor as pillow basalts. So that kind of explains those top two parts of the ophiolite sequence. So pillow basalts, and underneath are kind of the feeder structures for the pillow basalts, the sheeted dikes. What's a gabbro? You guys saw a gabbro. You probably saw it in your physical geology class. So what's gabbro?
Metamorphic rock.
Intrusive igneous rock.
Oh wow, that's how bad I am.
Intrusive igneous rock. What's the composition? Okay, remember you have granite, right? Granite is the intrusive silicic stuff, right? Really high silica, you get quartz, you get case bars.
It's a dark one. Just the pure.
So gabbro is basically basaltic magma that cools intrusively. So think of it as the magma produced down in the upper mantle. I just told you a minute ago, what happens to most magma? Never makes it there. That's where it ends up. So most of it sort of sits in this pool intrusively and cools off. Thing about gabbro, it has big crystals, right? How do you get big crystals? Slow cooling, right? Allows time for all of those molecules to hook together and bond and form big crystals. Where do you get slow cooling?
Where it's protected.
Where it's hot, intrusive. So the gabbros are kind of all the magma that was produced but didn't make it to the Earth's surface. It's one way to think about it. And then at the very base of this, you have the periddotites, that rock from the upper mantle. And that is the material we think gets melted. So sometimes you find periddotite that's nice and fresh and never melted. And sometimes you find depleted periddotite, stuff that has actually been partially melted. We'll talk about this whole melting, partial melting thing coming up here in a bit. But yeah, when you actually find them on land, they confuse geologists for the longest time. You find these typically along subduction zone boundaries, and they just don't make any sense. You know, you're out there and you're looking at all these rocks along a continent, and then you see all this stuff that looks like seafloor stuff, and that's exactly what it is. And it's little bits of the ocean crust that break off during plate tectonics, sometimes get rafted up on the land. So you can find these out around San Francisco, southern coast of Alaska, some older suture sections on Earth, but they're faulted, eroded, they're confusing. It took geologists a long time to sort of figure out what this was.
Don't they also have implications for the timeline of Earth?
Mm-hmm.
That's why. Okay, that's why.
And that's why you probably had it in paleo.
Yeah.
Right. Okay, let's stop there and we'll come back at 7. How about that? Give you a little break.